going to look at Chapter 14 now. Chapter 14 is gas turbine analysis. And gas turbines are the basis for jet engines, which we'll look at towards the end of the chapter. And gas turbines that we'll look at primarily are used in power generation. So they're very often used for emergency power generators and for topping systems. So very often there's you have a base load power plant, and then in the afternoon the power demand becomes high and you want something that will go on for a short time period, maybe a few hours, and you can use gas turbine units for that. And so we'll look at these. So we'll look at gas turbine units. They're used for power generation. Jet engines. And they're compact and lightweight. For power produced. So when we examine them, we'll look and we'll see, and this is one of the advantages. In a very small space, you can produce a lot of power. And so the actual system, so this will be for a power generation gas turbine. You're going to have a compressor. It's going to receive the air, so you'll have your air intake. It gets compressed and goes into a combustion chamber. So we're adding energy to this. It's going to come out of the combustion chamber and go into a turbine. And then it exhausts from the turbine. So state 3 and state 4. And part of what the turbine does is very often it's directly connected, so there's a shaft from the turbine going to the compressor. So part of the turbine work goes back and drives the compressor, and the balance is left over for power generation. So that, and perhaps this is 50 or 60% of the turbine power goes back to drive the compressor. And let's look at a TS diagram for this. And so ideally, we'd have isentropic compression from 1 to 2. So it would be compressing isentropically. Would then be adding, you have your fuel. This is P equals C, and this is where I have my Q dot N. And again, that's going to be burning fuel in the combustion chamber. We have the expansion through the turbine from 3 to 4. And then it exhausts at state 4, and typically this is P atmosphere. So state 4 and 1 are the same. And so now what we want to do is to create an ideal cycle for this. Let's look at, so this is how the power generation turbine works. Let's look at a jet engine. And it's slightly different, gas turbine. So here I have so part of it is I have the compressor the same way going into a combustion chamber, coming out and going into a turbine. So I have 1, 2, 3. But the purpose of the turbine on a jet engine is to drive the compressor and to have enough air pressure left over to go through a nozzle. So here's the turbine. It's going to go back, and its purpose is to drive the compressor. The air coming out of here, or the exhaust coming out of here, goes through a nozzle. So I have, and then it'll come out of the nozzle state, well, it'll be state 5, but I have 1, 2, 3, 4, 5. And so I have a nozzle, and I have air flowing through it, change of kinetic energy, and then you get the momentum principle, and you have a reactive force that it creates. So if I look at a TS diagram for this, going from 1 to 2, we have the combustion from 2 to 3. Now part of the expansion is from 3 to 4, and then I have from 4 to 5. And so from here, from 4 to 5, we have a delta KE, and basically the work from 3 to 4 is equal to the work from 1 to 2. So WT 3, 4 is equal to WC 1, 2. And that's your ideal model. And now what we want to do is, so this works this way, and we'll examine more of this towards the end of the chapter. We're going to go now and look at creating an air standard model for the gas turbine power generation. And that's called a Brayton cycle. Air standard model. It's a Brayton cycle. And what we're doing is we're replacing the combustion chamber by heat addition and the exhaust by heat rejection. So now let's look at that, and we'll have our compressor. Goes out. Now I'm going to have a heat exchanger, so I'm going to have heat in. Have a turbine. Still going to drive that, and I'll have my the network coming out of here. And then it'll go back through a heat exchanger, heat out, back here. And so we have state 1, 2, 3, 4. And so I have a mass that circulates around here. So I can have this mass circulating. And so I could draw a TS diagram for this. One to 2 is isentropic compression. Then we have constant pressure. P equals C Qn. We have isentropic expansion 3 to 4, and then we have P equals C heat out. And this is your network. So we have the network is there. And as you remember, that W net is equal to the sum Q. So for any cycle, we can say that. One of the things that characterizes the Brayton cycle is something called the pressure ratio. Just as with an internal combustion engine, we had a compression ratio. Here it's a pressure ratio. So it's how much the air is compressed between 1 and 2. So you have something called a pressure ratio. So R sub P is equal to P2 over P1. In the process, 1 to 2 is reversible adiabatic. And so we have that T2 over T1 is P2 over P1 to the K minus 1 over K is equal to R sub P to the K minus 1 over K. Qn, because it's constant pressure, Qn is equal to H3 minus H2 is M C sub P T3 minus T2, and Q out is H1 minus H4 M C sub P T1 minus T2. And so if I use the information, so if I look at here, I use the reversible adiabatic process from 3 to 4, it's going to be T3 over T4 is going to have the same R sub P relationship. So the T3 over T4 and the T2 over T1 are going to be equal, and I can combine that with these terms, and I can come up with the thermal efficiency for a Brayton cycle. So the thermal efficiency for the Brayton cycle is W net over Qn 1 minus 1 over R sub P to the K minus 1 over K. That's okay. And this is equation 14.4. So I wanted you to see that this R sub P thing comes out of this. I had temperatures originally, so originally it's temperatures, but it can be replaced very easily. So just as with the Otto cycle, which was a symmetric cycle, the Brayton cycle is a symmetric cycle, and we have a simple form for the thermal efficiency. And if I look at the thermal efficiency versus R sub P, we have something like K is equal to 1.66. So we can see that the only variable is K, and the lower the value of K, the lower the thermal efficiency for a given pressure ratio. So when I look at equation 14.4, this has no limitation on the upper temperature, on T3. So I just erased that. So I'll draw it quickly back again. That often happens. So if I look at the TS diagram, so equation 14.4, no limit on T3.